All right, now we are going to talk about association rule generation, right? So if we already have identified our frequent item sets, and now we will try to generate association rules from these frequent item sets, and we will look for rules whose confidence is bigger than or equal than the minimum threshold for confidence, right? So given a frequent item set, we can look at all its proper subsets and check if the rule X implies the set difference between f and x satisfies the minimum confidence requirement. So now let me maybe clarify something a little bit. So what is interesting here is what happens if we use the empty set as either the left side or the right side of our rule. Right? So what is the confidence of a rule that looks like this? F implies empty set. So what is the confidence of this? Now, by definition, this is the support of the union of F and the empty set, which is just the support of F, divided by the support of the left side. And the left side is just F, so support of F, which is 1. All right? Which is why it doesn't even make sense to consider rules of this type, so where F implies the empty set, because the support is of the confidence is always 1, so it just is not interesting. So, which is why we never ever include rules of this type, F implies empty set, into our analysis. So, on the other hand, if you find the confidence of the rule empty set implies F, then let's compute this, right? So, the support of the union is still going to be the support of F divided by the support of the left-hand side, and the left-hand side is the empty set. The support of the empty set is 1, right? So this is the support of F. And now it makes sense to include these into our analysis. So which is why when we do this, we require X to be a proper subset, which means that X is not F, but X could be the empty set. Could be. All right. So if the number of items in F is k, then there's going to be 2 to the k minus 1 rules to check, right? So we do not include the rules of the type X implies the empty set because the confidence is just 1. It is not interesting. So for example, if we have 4 items, so 2 to the 4 is 16, minus 1, 15. So there's going to be 15 rules. So we are going to try all possible combinations. So put some of A, B, and C on the left and the rest of them on the right. Now, hypothetically, of course, we could just try all of them, but a good idea is to do some kind of a pruning in the same in the same fashion as we did for item sets. And it is possible to do it. So and here is how. So the problem with it is that in general, confidence is not an increasing or decreasing function, right? So for example, if we compare confidences of these 2 rules, A, B, C implies D and A, B implies D, right? So notice that the difference between these 2 rules is that I just added C on the left-hand side, right? So they're not really related, right? So we can't say in advance which of them is going to be bigger than which of them is going to be smaller, right? So because look, because if we compare numerators, right, there's going to be support of A, B, C, D, and support of A, B, and D, and support of A, B, C, D is going to be smaller than or equal than the support of A, B, D. Same for denominators. Support of A, B, C is going to be less than or equal than the support of A, B. Right, so we're comparing 2 fractions, and we know that in both numerators and denominator of the first fraction are smaller than numerator and denominator of the second fraction. So the whole fraction can be either bigger or smaller, we don't know. So, but the good news is that the confidence of association rules is monotone in the right-hand side. So it's not a monotone. It's not a monotone function of the left-hand side, but it is a monotone function of the right-hand side. If we fix the union of the two, then it becomes a monotone function or an increasing function of the right-hand side, right? So here is why. So let me prove this little theorem. Now, so if x prime is a subset in X, right? So it means that the support of X prime is bigger than or equal than the support of X. Let me now find the confidence of the rule X prime implies F minus minus X prime. So this is going to be the support of the union, and the union is F, divided by the support of the left-hand side, which is X prime. All right, and this is going to be, now look at the denominator of this fraction. So the denominator is S of X prime. So if I'm going to replace the denominator with a smaller number, then the whole fraction can only become bigger. So this is less than or equal than the support of F divided by the support of X. And this is nothing else but the confidence of the rule X implies F minus X. Okay, theorem is proved. So here is the proof again. Okay, it means the following thing, right? So it means that if we have a rule that looks like this, I don't know, A, B, C implies E, G, X, something like this, right? If it does not satisfy the minimum confidence requirement, then if we take any item from the left-hand side and move it to the right-hand side, if we construct a new rule, A, C implies B, E, G, X, whatever, then it's not going to satisfy this confidence requirement either. And a priori algorithm for confidence rules is very similar to a priori algorithm for frequent item sets. So basically, it goes like this, right? So if we have a frequent item set F, then we want to generate all confidence rules out of this frequent item set. So we're going to place some items on the left-hand side and the rest of the items in F on the right-hand side. So first, we're going to go through all one-element subsets in F, all right? And then we're going to place these one-element subsets on the right-hand side of our confidence rule. And then we will compute the confidence. And we only include those whose confidence is above the given threshold. So those whose confidence below the given threshold are going to be just discarded. Then we generate all two-element subsets from H1, right? Put them on the right-hand side of our rule, compute the confidence, and basically do the same for 3 and so on and so forth. So it goes exactly in the same way as a priori algorithm for frequent item sets, only now with confidence rules, we're going to use confidence instead of support as a threshold, right? And we're going to put these items on the right-hand side of our rule and the rest of the items in F on the left-hand side of our rule. So here is an illustration, right? So suppose that, so we want to compute, to find all confident enough rules out of a 4-item set, right? So there could be a lot of them. So there are 15 of them. So the first rule is not really counted, right? So the one on top, because its confidence is always 1. It's not really interesting to count it. right? But then suppose that we have looked at, so we're going to try placing A, B, C, and D on the right-hand side, and the rest of these items on the left-hand side, right? And suppose that for one of these combinations, we found that it is not frequent, right? So if this is not frequent, it means that whatever contains C in the right-hand side and something else is not going to be frequent either, right? So this is not frequent, this is not frequent, this is not frequent. They all contain C on the right-hand side. So everything that contains C on the right-hand side is immediately out. It doesn't even make sense to consider them, right? But suppose that, for the sake of an example, that these are okay, right? So these three rules are confident enough. So now we are going to look at rules with 2 items on the right-hand side and 2 items on the left-hand side, right? And suppose that, say, this rule and this rule are confident enough, so confidence threshold is above the confidence is above the given threshold, but this one is not. But then, since here the right-hand side contains is AD, and here the right-hand side is ABD, which contains A and D, it means that we can just rule it out. So this is how it goes.